Hello, everyone, and welcome to the AQUALIS Sustainable Water Compliance Summit session addressing emerging contaminants in the water industry. I am Katie Johns, Editor-in-Chief of Stormwater Solutions, and I will be your moderator for this panel. To begin, I'm going to talk a little bit about how you can participate in this session. First of all, if you have any technical difficulties during this session, please put your question with the issue in the questions window, and our technical experts will help you. We recommend disabling any pop-up blocking software or extensions in your browser, as that can cause issues with the webinar player. Additionally, we welcome your questions during this session, and we'll answer as many as we can after the panelists have finished their discussion. But please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box on the side of your screen and hit Submit. Also, please be aware that today's event is being recorded, and you will be notified by email when the archive is available. At the conclusion of this webinar, you will receive an email with a link to download your certificate, which can be used to submit for credit with Stormwater University or serve as one personal development hour for attending today's session. Certificates will be sent to attendees who viewed the session for a minimum of 50 minutes, 50 minutes. For those viewing this session on demand, you will need to complete and pass a short quiz at the end of the session to receive your certificate link. And now let me introduce you to our session panelists. First, we have Rasha Malbared, Principal Environmental Scientist with CDM Smith. Dr. Malbared started working as the environmental microbiologist at the CDM Smith Bellevue Research and Testing Laboratories in September 2023. Before that, she was the wastewater treatment specialist and senior microbiologist at EPCOR Water for 10 years, where she supported monitoring, operations, and process optimization in 18 communities across Western Canada. She is the chair of the WEF Waterborne Infectious Disease Outbreak Control Focus Group, which received the WEF 2020 Water Heroes Award for their work on COVID-19. She also received the Empowering Women in Industry Leadership in STEM STEAM Award in 2020, the WEF Volunteer Service Recognition in 2021, and the Western Canada WEA WEF Laboratory Analyst Excellence Award in 2022. She serves as the current WEF Community Leadership Council Chair and lends her expertise to the editorial boards of Science of the Total Environment, Water Practice Technology, Frontiers Public Health, and Data in Brief. Next, we are joined by John Powell, PFOS and Emerging Contaminants Practice Lead at Black & Veatch. Mr. Powell currently serves as the PFOS and Emerging Contaminants Practice Lead for Black & Veatch and has over 30 years' experience in environmental chemistry, consulting, program management, business development, and laboratory operations. John has supported PFAS projects for 10 years, including drinking water treatment and mitigation, site investigations, remedial investigations, and programmatic support for the DoD. Working with the EPA and DoD, he was the project chemist for the development and validation of EPA 1633. And last but not least, we have Kyle Thompson, National PFAS Lead at Carollo. Kyle is a senior reuse technologist and national PFAS leader at Carollo Engineers, and he received his bachelor's in environmental engineering from Missouri S&T and his PhD in environmental engineering from the University of Colorado Boulder. Kyle is a professional engineer in Nevada and Texas. So with that, Kyle is going to kick us off. So the floor is all yours.
Thanks, Katie, and thanks, John and Rasha. Looking forward to your talks later in this session. So I titled my session "PFAS and Wastewater: Contaminants of Emerging, just kidding, Emerged Concern," because between when this summit was planned and when we're now holding it today, 2 weeks ago on April 10th, the drinking water maximum contaminant levels for 6 PFAS were finalized. And so Rasha will talk about later. There's different definitions out there for what exactly counts as a contaminant of emerging concern, how recently discovered does it have to be, how toxic does it have to be. But generally these different definitions, one thing they have in common is that when you're talking about a contaminant of emerging concern, you're talking about something that's not yet regulated. So with that federal MCL, I would say that PFAS, or at least the PFAS within that rule, have crossed that threshold, like one of those great white sharks from the Planet Earth documentaries they've burst through the surface and they have officially emerged. And I will say, well, that there's also the circle final rule, but that drinking water rule, that was for drinking water, but the EPA, they are also working on potential rules for PFAS that relate to biosolids and ambient water quality criteria that could then impact the MPDES permits for wastewater, even stormwater. So, well, it's the rule that was recently finalized. It is for drinking water. I do think it demonstrates where things are headed for the wastewater side as well. So, since I'm going first within this panel, I do want to have a little bit of PFAS background. I never know how much PFAS background to do these days as more and more people have become aware of these. So if you do know what's a PFAS, please refill your coffee and come back in 3 minutes. So basically, PFAS, it stands for per and polyfluoroalkyl substances, and it's a broad family of compound. There's different definitions out there, but generally it's organic compounds with at least a certain number of fluorines attached to the carbons. And the main PFAS, the ones that were, have the most regulatory attention, that kind of first got attention and that were, very widely used, these tend to be surfactants. So they'll have what they call a fluorinated tail, where you have a string of carbons that are all or mostly fluorinated, and then a head group that's typically an acid or negatively charged. And so that makes it a surfactant-like soap. And so these family of chemicals, they have a lot of unique properties that made them really useful for different commercial industrial applications. But unfortunately, kind of ironically, those same properties that made them useful are what's now making them a challenge for the water industry. So the carbon to fluoride bond is the strongest bond in chemistry. And so that makes these chemicals very resistant to heat, very resistant to oxidation. And so that's why, between being something that forms bubbles and something that's resistant to heat, that made them very, very useful for firefighting foam, for example. So these were used in firefighting foam for jet fuel, and they were practiced with regularly at both airports and military sites, where particular Air Force sites where they had jets, and they would do this firefighting practice. And since they practiced regularly, that was not a niche use. That was a very, very large use. But other examples, because they have this unique chemistry where it's repellent to both water and oil, so they were used in things like popcorn bags, Teflon pans, pizza boxes, stain resistant, and water repellent carpet and clothing. So a lot of different uses for these chemicals. And so the two main ones, the two that are sort of have the most evidence for their toxicity, and that states and federal agencies have generally moved on soonest, because they were used in large quantities first for many decades. They had the most studies on their toxicity so far. These were originally of the most concern. So sometimes when people say PFAS, they're talking about just these two. And so these are PFOS and PFOA. So these are pretty similar molecules. So in both cases, the O stands for octa, like octagon or octopus. So octa means 8. So they each have 8 carbons, and then those carbons are fully fluorinated. And at the end, they've got these different acidic head groups. So that's what makes them a surfactant, that they have the fluorinated part wants to be out of water, the negative part that wants to be in water. So just the main difference between these two is that PFOS, so the S stands for sulfonic, because it's got a little sulfur at the end there, whereas PFOA does not. So again, those were kind of the first two that were really widely used for many decades. I kind of call them the originals. So back over many decades, since World War II, through around the year 2000, particularly 70s or 80s, these were very common, and they were very powerful. So they're very powerful both in terms of their industrial uses, and also, unfortunately, very powerful in terms of their toxicity. But so around the year 2000, what started happening is the regulators and the public, for the first time, started becoming aware of the toxicity of these chemicals. So the companies that made them started to phase them out and come up with alternatives. They tried to come up with different molecules that could serve the same purpose industrially, but they might hopefully be less toxic or maybe break down in the environment. And so within this family tree of PFAS, you've got different divisions. And so one of these divisions is the long chains versus the short chains. So the PFOS and PFOA, like I talked about, those kind of is the long chains, but then you've got these short chains like PFBS. So you can see on the graphic there, PFOS versus PFBS. PFBS, it's literally just a shorter version of the PFOS molecule. Same end group, but just fewer carbons, making it a shorter molecule. And so the thing about it, if you have a smaller molecule, but with the same charge and similar other properties, it's inherently less, it's inherently more hydrophilic, so it's inherently less bioaccumulative, inherently less wanting to be in the human body. And so for the same exposure, it'll be in the body less, have less toxic effects. So the state of the science, at least for now anyway, is that these short chains, they're still pretty toxic, but they really are significantly less dangerous. And you can think of it kind of like one of those short little youngling lightsabers. But then that's not all they came up with. So another thing that they came up with was these polyfluoroalkyl substances. So poly, per is chemistry for all, poly is chemistry for many. So these polyfluoroalkyl substances, these are things that have many fluorines, but they're not completely fluorinated. So an example here is 8,2-dipap. So the 8 means it's got 8 fluorinated carbons, and then the 2 means it's got 2 non-fluorinated carbons. It's got a little phosphate there, and then the di means then it's symmetrical. It's got the same thing on the opposite side. And so you'll sometimes hear these called precursors, because the non-fluorinated part, it can biodegrade. So the fluorinated carbons, they're like non-biodegradable, but the non-fluorinated carbons can be biodegraded. So it can happen as you can have the non-fluorinated part can oxidize or biodegrade away, and then it will break down. So 8,2-dipap, kind of like Darth Maul's lightsaber splitting into 2, 8,2-dipap, it can oxidize or biodegrade into 2 PFOAs. And that's a pretty common PFAS, by the way, in popcorn bags and biosolids. But that's not all they came up with. So another alternative PFAS that was come up with, and so this was discovered in the 2010s, was this class of PFAS called the perfluoroethers, where the PFAS companies, they put in an oxygen with fluorinated carbons on ether side. And so GenX is the most famous of these perfluoroethers. So it was detected in large quantities in a river in North Carolina. And it's pretty interesting because not only is it a perfluoroether with that little oxygen in there, it's also got a little branch to it. So you can think of it kind of like Kylo Ren's lightsaber. It's got these little branches at the hilt. So all that to say, broad family of PFAS. There's infinite ways you can combine carbon and fluorine, but there's something like the EPA estimates over 1,000 PFAS that have been in active industrial use over the past decade, based on the EPA's PFAS definition under TSCA. And so, because these PFAS, they've been used in so many products. They've been used in shirts. They've been used in there's been cases where companies will fluorinate the insides of plastic bottles, like for household cleaning supplies, and then PFAS can be an unintentional byproduct of that process. So we don't really know exactly how much is why, but we know that there's PFAS that's been detected even in wastewater from single office buildings, even in wastewater from single homes. We did this literature review and looked at PFAS data from over 100 different wastewater treatment plants. And while maybe it was 99% detection for a specific one like PFOA, that one wastewater plant that didn't detect PFOA detected one of these others. So when 100% had detection of at least one PFAS out of the 129 in that literature review. And they are typically at levels, so the median levels for PFOA are at levels that would be higher than that drinking water limit, which makes them a really important contaminant to remove in contexts like potable reuse. And so, I want to talk about source control. So source control, so if you do have PFAS in your wastewater and you do need to reduce that, whether for state limits, so these potentially upcoming, there could in the future be this, they're working on the federal biosolids limit, they're working on the ambient water quality criteria that could then impact the NPDES permits. So the most cost-effective approach, rather than installing treatment to remove the PFAS, the most cost-effective approach would be source control if you can. So there's always some PFAS in wastewater effluent, but there are sites that have above average PFAS. And so if you have above average PFAS, then there's a good chance that you might be able to bring that down by doing some source control. So Corolla, we led a Water Research Foundation project, number 5082. So this is a big collaboration, including partners like CDM Smith, HRSD, SNWA, Purdue, Arizona State. So we led this Water Research Foundation project with the title on the screen there, and looked at how to investigate and potentially mitigate PFAS sources across wastewater, drinking water, groundwater, surface water. And through one of the deliverables of that project, kind of boiled down the lessons learned into a step-by-step guidance manual for finding and mitigating these PFAS sources. And so the 7 steps in that guidebook are laid out on the screen there, but I'm going to focus on step number 4, so interpreting results. So one of the things that we included in that interpreting results is saying, okay, so if I've got this PFAS data, so if I've got PFAS data in my effluent or in my biosolids, how do I know if that's just the base load, the domestic base load that's just kind of always there from pots and pans and t-shirts and kind of, really hard to take action against as a utility, versus if I have concentrations that would be some form of statistical outlier that would indicate that there's some sort of industrial source or point source in my collection system, or as I like to call it, a sewer shed, that I could then go investigate and place a local limit to bring those PFAS levels down. So the approach that we came up for having screening levels to determine, okay, whether this is likely industrial impacted or not. So you can't really assume that PFAS data is normally distributed, especially if you are talking about one of the PFAS where there's less consistently detected. If you have a lot of non-detections, then it could have inherently makes data not normally distributed. So there's this equation. There's this equation when making box plots. So this type of plot that I've got up on the screen, so this is called a box plot or a box and whisker plot. So you've got the center line that represents the median of the data, and then you've got this rectangle. So the ends of the rectangle are the 25th and the 75th percentile. And then this line, which people call the whisker. So this is biosolids data right now, not effluent data. But just as an example, so we did this exercise for biosolids and effluent. But so this line or this whisker, that represents the highest non-outlier. And so then they'll have dots or stars that indicate any outliers beyond that point. And so there's an equation that doesn't assume normality or anything like that. It's just 1.5 times the length of the rectangle past the 75th percentile is considered an outlier. So we used that outlier definition from box plots, and we applied it to different databases of PFAS data for both biosolids and the effluent. And so the previous slide, I showed a biosolids box plot, but this is the version of the table for effluent. And so it's three different databases here. So we've got the median and then the highest non-outlier for different PFAS based on these 3 different databases. So one of these was a literature review. So you do have a typo on the screen. So that Water Research Foundation Project 5031, that has actually been published now. So it was published 2 weeks ago. So if you're a Water Research Foundation subscriber, you can go download that report. So one of the databases was a literature review conducted as part of that project. Another was new data collected as part of that project. And the other was the data from the California statewide study. So this table, this is within the Water Research Foundation 5082 report, which should be online later this year. So you can so you can take your PFAS data, look at this table, and right away you can say, okay, am I close to the median? Am I typical? or am I above this, max non-outlier screening level that would indicate, oh yeah, I've got a industrial source of PFOS, and I could potentially look into that and try to bring down the level in my effluent. But what's interesting, so between these different databases, so on these bar charts, so the blue 3 on the left are the medians, and then the 3 bars on the right for each of these four PFAS are these screening levels that were determined. So they didn't really come out the exact same for these different databases. The results kind of depended on the database, but you'll notice these databases, these weren't collected over the same year. So the literature review database, it had data going all the way back to 1999. The new data for WRF 5031 was collected in 2020, and then the California data is the most recent, collected over 2020 to 2023. So if you line these up in chronological order, you'll see PFPEA, which is what's called a short chain PFAS. The screening level goes up, indicating the kind of typical range for that short chain PFAS may have been going up in recent years. And then the long chain PFAS, one of the long chain PFAS, PFOS, the kind of top of the typical range, is going down. And so that's actually wasn't too surprising. So if we take that data from the literature review and then merge it with the California data, so the literature review data is in the dark blue, California data is in the GeoTracker. So as part of that literature review, we found that the long chain PFAS were decreasing over the years. And then adding in the California data to extend the range of the years, it actually strengthened the statistical confidence of that correlation. So the long chain PFAS, so on the left there, PFOA and PFOS are going down over the years, and that's good, and that's expected, because as I mentioned, when the public and regulators started becoming more aware about these chemicals, the companies, they phased them out and started replacing them with these other PFAS, like short chain PFAS or polyfluoroethers precursors that can biodegrade into short chain PFAS. And so lo and behold, if you look over at the short chain PFAS, they got 4 short chain PFAS on the right there. So one of them is kind of basically holding steady, but 3 out of the 4 actually had a statistical trend up. So what we're seeing is, as the industry switches from the long chain PFAS to the short chain PFAS, we can see that reflected in the wastewater, kind of like how they were doing all that COVID source tracking and wastewater effluent. You may have seen studies tracking addictive drugs in the wastewater. So it's like a form of wastewater-based epidemiology, where we can see the PFAS being used by society reflected and the wastewater effluent concentrations. But overall, I would say this is good news, because as I mentioned, the short chain PFAS, they really do seem to be less toxic. Their regulations generally higher where they're regulated. So on the whole, this is good news. And maybe as we see more and more companies take more comprehensive bans on the PFAS that they use. So you'll see a lot of companies say, well, we're not going to use PFAS anymore, but then it turns out they meant just PFOA and PFOS, and then they'll refine their policy to try to eliminate PFAS more broadly from their products. So hopefully we may see some of these short chain PFAS go down too, because while they are less toxic, they are still pretty persistent in the environment. So we do still want to try to only use them where it's really necessary, anytime that something's highly persistent in the environment. And so I don't want to talk about too much. So I like to talk a little bit about solutions and good news. Don't want to talk about it too much, because I know John's going to talk about that. But just briefly, so the good news is we know it is possible to remove PFAS from wastewater effluent. So it's better to do source control if you can meet your goals that way. But we know, so out of the established treatment technologies for PFAS, reverse osmosis, granular activated carbon, ion exchange, we know from loads and loads of reuse studies, full-scale reuse implementation, we know that we can remove PFAS from wastewater effluent with RO and GHC, and there's studies going on right now at Hampton Roads Sanitation District, for example, where they're testing ion exchange for the content and PFAS removal in the context of reuse. So it is an expense, and it may take pre-treatment to kind of keep the organics load down on these treatment levels to the extent where if you're trying to remove PFAS from effluent, you're basically may end up with a reuse style of train just to have the cost-effective levels of pre-treatment. But so I think what I'd like my key take home to be is do source control if you can, but in the unfortunate event that we do have to resort to treatment, we do know how, thanks to reuse. And with that, I will pass it over to John.
All right, thanks a lot, Kyle. Appreciate it. So, following Kyle here, just what do we do for wastewater treatment for PFAS? So let's see here, go to the next slide, and a little background here, just to reiterate some of what Kyle said. As far as the challenges for treatment, are the PFAS chemistry, as Kyle mentioned, and everything. So you have this carbon tail for the PFAS, or the perfluoroalkyl acids that are fully fluorinated. But why is that important? And it's because the carbon-fluorine bond is the shortest and strongest known in chemistry. And these small fluorine atoms cluster so closely around the carbon atoms that they shield them from any chemical reactions, making them essentially non-degradable under normal environmental conditions and those found in a wastewater treatment plant. And the energy required to break the carbon-fluorine bond means that they don't offer a viable food source for any bacteria and will thermally degrade only at high temperatures. And the other important property of PFAS is they're negatively charged, as Kyle also mentioned, so they're surfactants, and so they can absorb to positively charged minerals or the sludge. The degree at which they will absorb is determined by the environmental chemistry and the chain length and the functional group that's associated with any particular PFA. In general, long chain and sulfonate PFAs tend to be more readily absorbed to the sludge, where the shorter chains and carboxylates and everything so are not. And the flip side to absorption is of course, in solution. And one of the unique things that some PFAS is that they're, in addition to being extremely persistent in the environment, some of them are very soluble, essentially, especially the relatively short chain carboxylates, as Kyle also mentioned. And this is why they pose such a risk to drinking water and can easily enter groundwater and travel many miles. And no biotic or abiotic degradation of PFAS means that, for an example, PFOA does not degrade into something else. If you have a precursor that degrades to PFOA, then that's the end of the reaction and it'll stay PFOA. So what do we do with these and everything? So, well, for the reason we just talked about, the fully fluorinated PFAS are not easily removed by conventional wastewater treatment methods. There are other PFAS, as Kyle mentioned, which are called precursors, and those precursors do break down or transform, but unfortunately they transform to the fully fluorinated PFAS, which can result in higher levels of PFAS, such as PFOA in the effluent, than what was normally measured in the influent. So your effluent's higher than your influent, and obviously that's more of an issue and a concern there. And there are also concerns that some PFAS are likely absorbed to the solids, and so the PFAS concentration in the sludge should also be monitored. EPA 1633, the analytical method that was recently or earlier this year published by EPA and finalized, is the analytical method for the analysis of wastewater, biosolids, and many other matrices. And many laboratories use this method as the TOPS method in combination to determine the total oxidizable precursors. And the total oxidizable precursor technique uses a strong oxidizer to transform precursors to their terminal products. So that 8,2-dipap that Kyle mentioned would then be transformed and everything, or oxidized in that process to the PFOA. And we would then, the laboratory would perform the 1633 analysis to determine the levels of the various PFAS in the sample. And these results could then be compared to the results of the analysis of the sample without the oxidation step to determine what could occur in the wastewater during treatment. Let's see here. And so often what we'll find with PFAS is that we need a separation technique to get them more concentrated to move over to a full treatment technique or destruction technique. So with that, one of the most common that's been tested recently has been the foam fractionation, and that takes advantage of the surfactant properties of PFAS. And it's gained a lot of attention lately and has been tested in numerous settings. The Department of Defense testing and EPA have both had pilot testing gone on and submitted the results to the further regulatory bodies. So in this process, air is bubbled through the liquid, which separates PFAS to the surface, and then the hydrophilic head of the PFAS orients in the water, while the hydrophobic tail orients in the air bubble. The rising foam is then separated from the liquid, which often goes through this process again to further reduce the amount of PFAS in the water. Because most PFAS, regardless of chain length, have a hydrophobic tail and hydrophilic head, they prefer the air-water interface. And so foam fractionation works pretty well for liquids with higher PFAS concentrations. And these include landfill leachate and many industrial wastewaters. Foam fractionation exploits these PFAS properties to absorb at the liquid-air interface of the rising air bubbles, resulting in the foam formation at the top of the foam fractionator. And the removal of PFAS is then achieved through foam harvesting, and the foam fractionation is then increasingly concentration of the wastewater is then moved through the process and resulting in simplicity and lower operational cost. And the coupling of foam fractionation with destructive technologies is potential to have a comprehensive treatment train. So we'll move on here. So what are some destruction technologies? We certainly don't have time to cover all of them, but we'll hit on just 3 of the ones that have been gaining a lot of attention lately. And the first one here is supercritical water oxidation. And it is a physical thermal treatment process powered by water above its critical point, or 374 degrees Celsius and 221 bars of pressure. And at that temperature and pressure, the air yields a highly effective oxidation reaction that completely destroys organic compounds. Reaction generates energy and byproducts that can be recovered and potentially reused. The supercritical state of water is a special state where organic solubility increases and oxidation processes are accelerated. Supercritical water oxidation, or SCWO, has been previously shown to destroy hazardous substances such as chemical warfare agents, PCBs, and other halogenated compounds. So it's promising technology for PFAS, and there's several companies now that are pilot testing this out in the field. So the next technology we'll touch on is electrochemical oxidation. And this is where electrical energy is introduced into a liquid to break the fluorine bond, the carbon-fluorine bonds of the PFAS. And not all electrodes are equally effective, and there are a number of different technologies out there, companies that are testing their particular electrode. And there are very few that are commercially available, but there are under development at this point in time. And some PFAS precursors will transform to more recalcitrant end products. However, the precursor transformation will occur with most, if not all, destructive technologies. Electrochemical oxidation also oxidizes everything else in the water, so energy usage and effectiveness are affected by co-contaminants or dissolved organic carbon in the liquids. And we'll move on to plasma technology, which is another one using electricity to convert water into a mixture of highly reactive species. So the hydroxyl ion, hydrogen peroxide, and other ions there. And the plasma is formed by means of electrical discharge between one high voltage and one ground, or contacting the water. And in this process, argon gas is pumped through a diffuser to, again, bubble the PFAS to the surface, where at the surface, surface layer then is oxidized. And for this reason, let's see, with all of these treatment technologies, it's important to perform sampling analysis of all the matrices, the water, the soil, or the solid, and air to determine where the PFAS are going. So you want to make sure you're just not transferring the PFAS from one media to another. So, and then for this reason, a mass balance is suggested and was actually noted in the EPA Destruction Technologies guidance document that was published just a few weeks ago. And we'll move on to, in summary here, the 2024, as we've seen, has been a year of change. We wrote the slide a few weeks ago, but we've definitely seen a lot of change here just within the past month with different regulations issued. And also, as Kyle mentioned, and everything. So it's important to do assessment of the industrial users and what's actually coming into the wastewater treatment plants. So, and work with those industrial users to try and reduce the PFAS discharges at the plant level to be much better on the wastewater treatment plant and reduce the need and everything for the treatment there. And also engage stakeholders, lawmakers, and industry groups, because it's important to engage with them early as opposed to later on and everything. So then find that the regulators not necessarily liking what's going on with the process that you're designing. So with that, I'll hand it over to Rasha.
Hi, everyone. Thank you for that, John and Kyle. So my colleagues here gave you a really great overview about PFAS and some of the treatment technologies and challenges associated with it. So what I'd really like to do is maybe take a step back and look at contaminants of emerging concern in general, using a case study, so microplastics specifically, and then maybe look at the lessons learned from PFAS and how we could apply them to other CECs. So when we try to define CECs, we very quickly realized, just as Kyle pointed out, that there is actually no standard definition. Different organizations define CECs quite differently, although there is a little bit of overlap. So the majority of definitions will basically talk about risk to human and ecological health, whether that risk is potential, actual, or perceived. The other thing you'll notice about CECs is that they're often focusing on changing regulations or changing toxicological limits. Some of them are new, some of them are older compounds, but our understanding of them is changing. And again, the issue of having that public health limit, that protective limit. So many CECs do not have an MCL, for example. And as a result of that, if you're looking at different CEC lists for different organizations, those aren't static lists. They change, they get updated. And over time, we start seeing maybe some compounds that we haven't seen in the past. It's really important to recognize as well that CECs are a very broad group of chemicals. So they can be synthetic like PFAS or naturally occurring like cyanotoxins. They can be chemical or biological in nature. But overall, you'll notice that they do tend to lack standard methodologies. We develop those standard methodologies as we go along, but as you saw with PFAS, it took us a while to get there. Some proactive water resource recovery facilities and water treatment plants will be looking at testing CECs in their sources, in their effluent, and they will be detected at trace amounts. But overall, we rarely do tend to test for them unless it's a research collaboration or a proactive effort. And I've added a list here of some of the CECs you may have heard about over the last few years, decades, and so on. I think the ones that will catch your attention the most are probably the endocrine disruptors, maybe the pharmaceuticals and personal care products, and definitely maybe 6-PPD, which again, we became familiar with as a result of Shane Snyder's work and sort of the heightened awareness of its fairly dramatic toxicology. For today's purposes, again, I'll focus on microplastics because I do think it's a very relevant CEC for the stormwater community. So microplastics are traditionally those plastic debris particles that are smaller than a range of sizes. Again, going back to that issue of not having a standard definition, different sources will say they have to be smaller than 1 millimeter, 3 millimeters, or 5 millimeters. You might be going, well, how small do they get? Well, once they hit 100 nanometers, so less than 0.1 micron, now they're called nanoparticles. And we won't talk about nanoparticles today, in part because there's actually very little we know about nanoparticles and their impacts on human health and so on. Just like with CEC definitions, there was no standard method for microplastics until the California Water Board kind of took that on as its mission. Now there is an analytical method that's focused on drinking water, microplastics enumeration and characterization. But you'll also notice that that method was not focused on sampling. So Water Research Foundation actually added a project more recently to try and develop that sampling methodology. And the million-dollar question, do we actually remove microplastics? And the numbers are somewhat misleading because the literature very clearly says that we remove anywhere between 95% to 4 log reductions of microplastics. But what we know for certain now is that those microplastics end up in our solid streams. So while our effluent might have less than 1 all the way to 30,000 microplastics per liter, we see much more contamination in our sludge and biosolids streams. And the reason we care about them is because that risk factor that we just mentioned. So there's 4 pathways in which microplastics can potentially cause risk to consumers. The first one is sort of the direct physical impact of consuming a particle that is plastic. To this date, we haven't seen a lot of evidence that there is a detrimental effect to that. Pathways 2 and 3, however, there's been quite a bit of evidence to suggest that microplastics, because of their surface properties, have the capacity to bind chemicals. So chemicals will absorb, other CECs will absorb to their surface. So there's been quite a bit of studies about PFAS and microplastics co-transport. The third pathway, which is basically the idea that your microplastics production potentially involved some CECs as well that could leach out of the product itself, and those could result in an adverse health effect. And then that final part, and that's the fourth pathway, where the surface of the microplastic can be colonized by microorganisms that can be toxic, as in pathogenic, and they can then potentially also produce toxins, all of which obviously result in potential need for more investigation and regulation. So how do they enter our water systems? Well, we all know this already. There's nothing new here. It's point sources. So those are, let's say, water reclamation facility treated effluent outputs. We know there's non-source point sources, and that's your runoff and so on. There's some that are associated with particles, biosolids, and so on that can reach your water body in a variety of ways. And then there is those accidental spills that we're starting to see a little bit more frequently, as well as natural disasters that result in more release of those particles. I think the one that we have the least information about and where there's actually pressing need is atmospheric deposition and particles, rain, snow, and so on, how much they're contributing in terms of volatilized CECs. This is important in part because we know that there's a whole range of variables that impact how much we care about CECs, how willing we are to try and control them. The first one is, of course, the fact that water is connected. Doesn't matter where you're starting. Kyle, you said it perfectly. We're talking about MCLs for drinking water now, but eventually it will impact water reclamation facilities permits. We know that science and technology will impact whether we detect a CEC or not. Our detection limits are becoming more and more impressive, but the question often rises, well, at what level is there risk if we're basically measuring trace amounts? There's cost-related questions. If it was cheap to remediate, it's a much easier task for us to address them, but that's often not the case, and there's that question of risk. We, as water professionals, see ourselves as water, public health, and environmental health protectors, right? We take that very seriously. And then there's that aspect that's risk-related, but that kind of has a lot more to do with how we reach out, that outreach, that communication. That's the public connection to CECs, their awareness of what's going on, the media, how it's reflected, the CEC reporting that's happening, regulations. Once it's regulated, we are monitoring for it. We have no option, right? And then that climate resiliency, where climate change is forcing us sometimes to look outside our comfort zone to try and come up with solutions. CECs are part of that because water scarcity is part of climate change. So let's rephrase that very quickly in terms of what you've already heard from John and Kyle, lessons learned from PFAS. And they actually do apply to a whole range of CECs that are not regulated yet. But again, we could be more proactive in that case. So when you think about OneWater, we know that partitioning matters. Both Kyle and John said to you, PFAS is sometimes in your liquid stream. It does adsorb to solids. With microplastics, we know they're in your solid streams. So this matters in terms of management options and solutions. Source control, both other speakers have mentioned this because it is a very critical part of how we manage the risk and the issues. When it comes to science and technology, of course, as we mentioned, the lack of standard methods is a huge issue. PFAS, we were challenged until the standard methods started coming out. So that is one area where we could be doing better, proactively working, just like California did with microplastics, and getting lower detection limits, right? We are in an interesting situation now where the MCLs are so low for PFAS. We don't know where some of these MCLs might actually come in. So being able to prepare for that is very important. Cost, the CapEx and OpEx actually is quite tremendous to treat PFAS compounds in our water systems, right? But what's more, I think, a challenge for us as an industry is the fact that we're shifting that cost, that burden to utilities and to ratepayers. So we've seen that with PFAS. Is there something we could do differently to prevent that in the future? Risk assessments, that is definitely something we would like to do a little bit more standardized. The EPA may not have completely followed its own process. At least a few organizations have shown concerns with that process. And protective limits. We don't know much about chronic exposures, sublethal exposures. Then there's a whole range of other topics related to the public and citizen science, which we're seeing more and more frequently now. I like citizen science. I think it needs to be supported and facilitated by subject matter experts. Similarly, when we're dealing with the media, utilities don't do communications well a lot of the times. Some excel at it, many do not. So having communications teams is critical, and translating the knowledge so that those communication teams can do their job is very helpful. I think we saw very much with PFAS that sometimes it's not about the science. Regulation is influenced by other factors as well. And then finally, that climate change issue where I think water resource recovery facilities and drinking water treatment plants want to prioritize to adapt and become more resilient. But sometimes with CECs, our priorities shift, whether we like it or not. It's a very complex picture, and I look forward to having that discussion with the panel. So, Katie, I'll hand it back to you.
Thank you so much, all of you, for sharing your perspectives on contaminants of emerging concern. We have a few minutes to have a discussion. And as you've all mentioned, the last month has been full of PFAS news, especially with the new MCLs. So I do kind of want to spend some time on that. I think we would be remiss not to in a panel like this. So I'm wondering if each of you can kind of share your initial thoughts on those new MCLs and what you think that means for the industry. You can decide who would like to.
Sure, I can. I can speak to that. So I'll say, comparing the final rule to the proposed rule, a lot of people were hoping that they might revise the PFOA and PFOS limits upward from 4 nanogram per liter to 10 nanogram per liter. That would have been a bit more cost effective at that level, at least a lot more clear, and the cost benefit compared to what they went with. But a silver lining, I do want to put a positive note. The silver lining was one of the big changes was the extension of the compliance window from 3 years to 5 years. So that was a big sigh of relief, particularly for large systems. So smaller systems, they can use these prefabricated modular vessels, but for large systems where you're talking 50, 80 of these vessels, it could be better to do a concrete gravity driven contact basin for the GAC, and infrastructure like that takes a very long time to construct, especially if you are going to do treatment studies first, especially when you do you can do RCCTs, but if you do choose to do a pilot, then that can take a very long time. So really will, and then also with the unprecedented demand for these treatment technologies, that could make these things take even longer than they have in the past, right? So it's a big sigh of relief to have that 5-year compliance window. And then I did hear confirmed in a EPA webinar yesterday. So before it was 3 years with the potential for a 2-year extension. So a 2-year extension is still on the table, even with that extension of the kind of main compliance window from 3 years to 5 years. So I think that's the silver lining for the drinking water industry.
Yeah, I would agree. And I think the silver lining there is the extension, because as Kyle mentioned, this will be, an incredibly costly endeavor to try and hit those MCLs. The MCLs, fortunately, were somewhat as expected. That didn't change there. Hoped for that they might be elevated, but they are achievable. Just with potential supply chain issues, I imagine those extensions will be needed. And also a costly endeavor. So fortunately, there is some funding available. So trying to find the necessary funding for these, because plant modifications are so expected. I saw recently, one plant is talking about $100 million, another one plus a amount a lot greater than that, 250 million dollars from one city. So.
And maybe I'll put on my utility hat in this specific case. So I agree. I think there's silver linings. The 5-year certainly helps compliance likelihood. And there's benefits in and of itself to having EPA come out with federal guidelines at a time where there's quite a bit of heterogeneity in the different directions different states are taking. I do want to reemphasize maybe that there are potential implications here for ratepayers in terms of these costly solutions, regardless of whether or not we're starting with drinking water or not. Kyle, you said it will come down to the permits eventually for the water resource recovery facilities. And unfortunately, traditionally, the ratepayers that have the least flexibility on increasing rates are the ones that do tend to be hit the most. So I do wonder about that a little bit.
Yeah, definitely. That's all very good insight. And we only have a couple more minutes. So I kind of want to, because you've all touched on some of the challenges and what's on the horizon. So I'm going to skip a little bit to innovation-wise. Do you think these new MCLs and other contaminants of emerging concern are spurring innovation in the industry? And if they aren't yet, should they be?
Well, I'll go ahead and answer Rick's first here. I think, there have been a lot of things, technologies in development for a number of years. They've been doing bench scale testing and limited pilot scale testing. I imagine that will increase significantly now that the actual MCLs are out and the other drivers and everything behind, that with the MCLs, then they'll come out with regulatory values for the Clean Water Act. I imagine will come down the road as well, groundwater limits. So that all of those coupled together will then drive the technology and drive more companies to do additional testing. I know the Department of Defense has been doing quite a few pilot testing through their CERTIP ESTCP program, and I imagine that will continue there as well as move on to the industrial side as well.
Yeah, I would echo John's last point there, that I think part of the difference that we've seen for PFAS compared to other emerging contaminants of emerging concern over the past 20 years, since one of the major sources was from military sites, the Department of Defense, to their credit, has made major investments in research on the treatment and detection of PFAS. And so, having that, and it's on top of the, traditional environmental research funding sources like the EPA, has really driven the really fast pace, at least by, for as far as, the water industry goes, very, very fast paced innovation on this topic. New studies, left, right, and center on new ways to destroy, separate, or detect PFAS. So it's really really exciting to try to stay up to date and all that. And I'm a little skeptical of some of these destructive technologies. At least for like large drinking water plants, they're just a little bit over, at least not without some prior separation. But there's a lot of these novel sorbents coming out that I think are really promising, and I'm really excited on the novel ways of detecting PFAS too. I think it's a really exciting upcoming research area.
I would agree. Certainly the last startup call even had a component in there for microplastics. So I think there's a lot of awareness about the CECs that are emerging, and very heightened risk awareness. I'd love to see more natural solutions, to be quite frank. That is an area where we could be doing a little bit more of a proactive job. Some very interesting work on wetlands and PFAS absorption, biomagnification, but we could be doing more in that area.
Absolutely. Well, I am afraid we have run out of time for today. I know we didn't get to audience questions, but we will be sure to answer those offline when we are able. Just a reminder that at the conclusion of this session, you will receive an email with a link to download your certificate to use on Stormwater University or as one personal development hour. So that concludes our session. Thank you so much, John, Kyle, and Rasha. You guys gave us some really great insight, and I'm very appreciative. And to our audience, don't miss our next session in today's summit, Green Infrastructure Planning, Implementation, and Maintenance Program for a Needs-Based Approach. Or there's a session on a digital OneWater approach to collection system asset management. You can join either session by exiting out of this event and going back into the agenda, then select the session you'd like to join, and you'll be in. So thank you all so much, and have a great afternoon.